Professor Clements with you as we discuss Chapter 19, Section 1 in the OpenStax College Physics book. Chapter 19, Section 1, dealing with electric potential energy and potential difference. There's an analogy between the electrical case and gravity. In first semester, we talked about masses that go towards the center of the Earth. They can give up potential energy, gravitational potential energy, MGH, for near the surface of the Earth, and that can become an increase in kinetic energy. A similar thing can happen in the electrical case. Consider this charge plus Q, and we're going to release it from rest. It'll move off to the right because it's repelled by the positive charges. It's attracted by the negative charges, and it will gain kinetic energy. It is giving up potential energy, electrical potential energy, when it does this motion. So that's an analogy that we have there. You do need to be careful of wording and symbols in this section, in this chapter. Electric potential energy is not the same thing as electric potential. Potential energy is measured in joules, and potential is measured in volts. So with that being said, let's go ahead and consider some action here. The charge here would be moving off to the right. It'll gain speed. We can actually say that the electric field is doing work on this charge as it moves across here. And we could calculate the work as Q times the change in voltage that the charge moves through. And someone would have to tell us the magnitude of the charge, the voltage difference from location 1 to location 2, but we could calculate the work in that situation, and work can be positive or negative depending on the situation. So in this case, work is done on the charge. It builds up kinetic energy. In the reading guide that is available, you'll see some definitions, some calculations. We can calculate the voltage. If we know the potential energy and we divide by the charge value, we could calculate the potential at one location. We're not going to do that too much. A future section is going to show us how to calculate potential, and there's some examples in the PDF files that are available that shows how to calculate potential. But we will be often interested in the voltage difference between two locations, and then multiplying Q by the voltage difference will allow us to calculate the work done in moving across that situation, and also the potential energy in that situation. So when we label things, very often we'll put 0 volts at the negative terminal and some positive voltage at the plus terminal. That's not a requirement. Just as in mechanical motion, the 0 point of potential energy does not matter in solving the problem. It makes it more convenient. It's only difference in the potential that is going to help us solve the problem, difference in potential energy as well. So very often we can assign 0 for the negative and some positive voltage for the plus plate here. There are some examples in the textbook that you should take a look at, and we're going to just discuss an electric car battery for a moment here. Work is done in a chemical process inside the battery to move electrons towards the negative terminal. It does require work. We're moving a negative charge away from a positive terminal towards a negative terminal, moving a negative charge, the electron. So it does require work, and that gives the charge a potential energy. If we connect a wire through a light bulb, we can release that potential energy into work on the filament, raise the temperature of the filament, and the light bulb shines. We'll talk about currents in a future chapter. But we will let charges move in this chapter. It won't be quite so static as previous chapters. Another illustration here. Here we have a negative charge, an electron. It'll be repelled by the negative plate attracted to the positive plate, and it will gain kinetic energy as it moves across here. The kinetic energy gained is equal to the work done on the electron. And be careful right in this notation with this QV. This V is the difference in voltage between the two plates. It is not the potential at one particular spot. The tradition, the understanding here, Q times change of potential, gives us the calculation for the new kinetic energy of the charge, assuming it started from rest. Very often in atomic physics, we'll use the unit of electron volt for the energy instead of joules. If you would, let's say it's 10 volts across here for the potential difference. If you put in 1.6 times 10 to the minus 19 coulombs, then you could calculate the energy in joules. That's a lot of power at 10 work. So with electrons, we might just put in 1 for the charge, 10 volts here, and we'd have 10 electron volts of kinetic energy. In the paragraph, they're saying that there's 5,000 volts potential difference between the two plates, and consequently Q times the change of potential moving from 0 up to 5,000. We would have a calculation of 5,000 electron volts, with Q being 1 if there's just one electron that's moving across here. So the electron volt is a little easier number to work with, dealing with electrons and protons. Electron volt is a unit of energy, and there's conservation of energy occurring here. This electron has a potential energy in its configuration near the negative plate. It gives up potential energy, it gains kinetic energy as it moves across. So there's a little introduction for the concepts of potential energy, and work. The big concept, work, is equal to the charge that's moving times the change in potential. I'm trying to draw a delta here. And again, the context, this V and this delta V mean the same thing. You have to be careful with the notation. It's traditional notation. It's a little misleading. It is Q times change in voltage, change in potential, that's important in calculating the work that's done. So with that, we're going to stop our discussion of section 1.